Hello, my name is Mathieu Cunche. I'm an associate professor at INSA Lyon, and I'm going to present you a joint work with my former PhD student, Guillaume Celosia. So this work is about Bluetooth Low Energy continuity protocols that are used by Apple devices and the kind of privacy issues that you may have with those protocols. So first, what are Apple continuity protocols? So Apple continuity is a family of services provided by Apple devices such as AirDrop, Apple Pay, Instant Hotspot, Handoff. So Handoff is a tool that can use to transfer one activity such as writing an email from one device to the other. So those continuity protocol, the main purpose is to enable interaction between nearby devices. And how it works in practice is that they leverage Bluetooth communication to carry information between nearby devices. So it's more specifically, it's Bluetooth low energy that is used here. So if you need to transfer an activity from one smartphone to your laptop, this will be done by transferring some data over Bluetooth low energy. So more particularly, what kind of messages are used for that? They use Bluetooth low energy advertisement packets. So those packets are transmitted periodically by Bluetooth low energy devices in order to announce their presence. But in addition, the Bluetooth consortium enable the possibility to include custom data in those packets inside the manufacturer-specific fields. And this is what Apple did. So they use this manufacturer-specific fields to include their data used by continuity protocols. So inside the fields used by Apple, you will find continuity messages, potentially several of them, inside this same field. And each of those continuity messages will follow a type length data format. So those messages, they are broadcasted in clear, so there is no encryption on that. Means that the information is available to any eavesdropper, and this has been noticed by several works that have identified serious privacy issues associated with the use of continuity protocols. Most of those works, they present tracking attacks in which an attacker can track a device over time because there are some identifiers that are included in those messages. However, those work, they only discovered the tip of the iceberg with regard to privacy issues because they only had a partial understanding of the messages. And what we did in our work is to reveal the rest of the iceberg by discovering the full meaning of the continuity messages. So we wanted to understand what were those continuity messages, meaning to basically understand the language of Apple devices, how they talk over Bluetooth. The problem is that those messages, there is no public documentation about it. So there is little information. The software is closed source, and you will find no documentation almost from Apple. So what we did is we had recourse to reverse engineering to understand what were the meaning of those messages. We first had a look at Apple debugging tools to reverse engineering those messages. Then we also crafted our own continuity messages, and finally we made a bit of disassembly of some of the binaries involved in continuity protocols. So the first tool that we used was provided by Apple. It's called Packet Logger and Packet Decoder. It's a debugging tool that will parse and log messages incoming on your device, including the Bluetooth messages. So for each message, you will have the meaning of the message as well as some potential actions that are triggered by the reception. So it was really useful to get a first glimpse of what were those messages about. Then we had recourse to crafting our own continuity messages. So using HCI tool, we generated custom messages based on the templates of messages we've already observed, and we broadcasted those messages over the air, and we observe action that were potentially triggered on nearby devices, but most importantly, we had a look at how they were interpreted by packet logger. So this was another good source of information to understand the meaning of those messages. And finally, we did some disassembly. So we selected a number of binaries, and such as core speech used by the Siri voice assistant, sharing D involved in the airdrop functionalities, also packet decoder and packet logger, the two tools I've talked about, and other softwares like HomeKit accessory simulator. And what we had, it was pretty neat. We managed to get the information on all the messages, so the format of those messages, but most importantly, the meaning of the codes. So for instance, in our case here, what I'm presenting, the code I'm presenting is related to the passing of one message that is called action and can have many types. Here I'm just listing the first types of this message. So for instance, if the value is 3, it's for mobile backup, 4, it's for watch setup, and 5, it's for Apple TV pair. So we had, thanks to those 3 approaches, we managed to get pretty good view, and what I can say is almost all the, we basically understood everything, all the language of Apple continuity. So what we had was the understanding of all the messages. So we had a total of 10 messages type. For each message, we have the format of the message, so different fields composing this message, and also for each field, the meaning of the code. Sometimes you have some codes in there. So a lot of information that is listed and available inside our paper. So now we understand fully the language of Apple devices, and we are ready to start investigating for potential privacy and security issues. So we discovered many things, but in this presentation I'm just going to talk about 4 of them. Physical tracking, so how you can track users, spying, how we can spy on the smart home activity, how some emails and phone numbers are leaked, and finally the case of Siri spoken comments. So let's start with the physical tracking. So physical tracking of BLE devices and their user is possible because those devices, they broadcast periodically advertisement packets, the packets in which Apple continuity messages are included. And those messages, like any Bluetooth messages, they include a device address, which could be used to track the user, the device and the user over time. So to limit this risk, the Bluetooth consortium has included inside the specification the possibility to use random addresses instead of the real address. So periodically, the device will switch to a new random address, and doing so, it will prevent any passive attacker from tracking the device over time based on the device address. So this is a good thing, but this is only about the device address, and many works have shown that if you include all the data inside those advertising packets, your device could still be tracked. For instance, inside continuity messages, we identified that the AirPod devices and along with the case broadcast continuity messages in which you have information about the state of the AirPod sets. So basically the battery state and the number of time the case has been opened. And all this is advertised in clear, of course. So here we presented on this figure the evolution of the device address, how it changes over time. So the vertical gray and white stripes are the device address changes. So the device address is changing every approximately 15 minutes. And you can also see the lead open counter and the different battery levels of the device. And if you look at the lead open counter, you can see that this value remains the same for a period that is way longer than the duration of a device address. So this could be used to link two consecutive random addresses. Same thing for the battery level. It stays the same for a period that is longer than the duration of 15 minutes used by the random address. So based on the artifact broadcasted inside those messages, it becomes kind of trivial to link consecutive addresses of a device, and so you can defeat the purpose of address randomization, and you can track a device and its owner over time. So, but there are other examples of issues in the paper. Second thing I want to talk about is how we can spy on smart home activity thanks to the messages emitted by smart home appliances. So Apple has introduced HomeKit, so it's a framework for smart home. It's used by Apple devices, but also by other vendors. And each device using this framework is periodically broadcasting continuity messages in which you have a global state number. And this global state number is basically a counter that follows the state of the device. So whenever the state of your device changes, this counter will be incremented. So whenever, for instance, in the case of a light bulb, whenever you turn it on or off, the global state number of your light bulb will be incremented. So by observing the evolution of the global state number, you will be able to see if there is any activity inside the house, and you can see which devices are used by the occupants. So it's pretty invasive. So to test, to see how we can do that, we conducted a small experiment in which we had a smart light bulb and a presence detector. And we both placed them inside our office, and we monitored the messages from outside the room and observed what we managed to get. And this was pretty obvious. So here I'm presenting the evolution of the global state number. So each spike here represents a change in the global state number, either for the motion sensor or the light bulb. And you can see that based on this indicators, you can see when we arrive at the office, when we leave the office, also the lunch break we had during the day. And you can even detect when the janitor is entering the office early in the morning. So by remotely and passively listening to Billy messages, you can have a quite good idea of if there is someone inside a smart home and what this person is doing. So it's a bit scary. And of course, all these messages are broadcasted in clear, so there is no security to break here. All right. A third point I want to discuss is the cases of the airdrop messages and nearby action used for Wi-Fi credential sharing, in which we found that there are identifiers that are included. So those identifiers are not included in clear, they are hashed. And why do they include identifiers in there? It's for friendly device identification. So for instance, if you want to send a file to the device of a friend, before establishing the connection, the devices will make sure that the owner knows each other. So you will send your identifier and the recipients will look up inside the contact list to see if there is a matching identifier, so if you know the person. So those identifiers are not sent in clear. As I said, they are hashed using SHA-256, and then later on they are truncated either to 16 bits in the case of airdrop or 24 bits in the case of nearby action for the Wi-Fi credential sharing. The problem is, as you know, that hashing is not a good way to protect identifiers. In fact, many works have shown that you can reverse this hashing using a guesswork. Basically, it's a brute force attack in which you try all the possible identifiers. And this is what we try to evaluate using hypothetical attacks. So we did not perform these attacks, we just estimate the cost and the success rate of those attacks. So we considered hypothetical sets of phone numbers and email addresses of various sizes, and we computed the amount of time that it would take to test all the values. As well, there is another thing to consider is the number of matches, because when you compute the hash, you fall back to either 16 bits or 24 bits. So it's for in the case of 16 bits in particular, it's quite a small set. It's 250 to the power of 16 different values, which means that if you have a set that is larger than that, you can have ambiguity. So several identifiers matching the same hash, so you will not know which of them is the correct one. So we evaluated those two metrics. So first, the guesswork time, the attack time is, pretty easy to achieve. In the worst case, we have a computation time of 1 hour, and in the base case, it's less than 1 second. But also we looked, so computation is not a problem. The only problem is the number of hashes that will match. So in the case of a 16-bit identifier, you have a matching set that is quite large. So for instance, you can have more than 70,000 matching identifiers, which is not very practical. But if you have 24 bits, you have much smaller sets that can be used to narrow down your search. So for instance, you can try all the phone numbers registered, the landline phone numbers. In average, you will have only 2 matches with the 24 bits identifier broadcasted by the nearby actions. On the other hand, if you looked at smaller sets like for email addresses, like the users inside a university department, like 7,000 users, here you will have only 1 match that will happen. So this shows that depending on the set of the size, you will be more or less successful at identifying uniquely the user. In practice, this shows that you need to prepare your work and to target a bit your user. But for instance, if you are in a small group, that is quite easy to do. And the last point I'm gonna briefly discuss is the case of Siri messages. So Siri is the voice assistant used by Apple. And we discovered that whenever you talk to your device, your phone, whenever you send a command to your phone in parallel will broadcast a continuity message in which you have a hash, a perceptual hash of the voice command you've just spoken. So these perceptual hashes are not like cryptographic hashes, in the sense that if there is a small variation in the input, so a small variation in your command, there will be a small variation inside the hash, or sometimes if the variation is small enough, there will be no changes at all. So it's basically those perceptual hashes, they are used to identify comments like voices or images to this kind of signal identification. And so how it works is whenever you send a voice command, it will take the audio signal as input, put it through the perceptual hash, and output the 16-bit hash that will be included inside the message. So again, as for the email addresses and phone numbers in the previous section, here we could try to see if, based on the hash that is sent inside the Bluetooth messages, if we could try to reverse it to the original comment that was spoken by the user. This means that you don't need to listen to the voice command, but you can be outside the house, listen to Bluetooth messages and try to pick up those perceptual hash and try to infer what was the command spoken by the user. So we try to do that. The results are not great at for now. The problem is that 16-bit hash is quite small. So again, there is a lot of ambiguity. But if you can shortlist a number of comments that you want to test, it is interesting. So the performances are not, as I said, not great, but I believe we could improve that. And you could infer what is spoken inside the house just by listening to the voice comments. The voice, sorry, the barely messages sent by your Siri device. All right, this was the last attack I was going to talk about. Now let's move to the conclusion. So in this work, we presented a full reverse engineering of the Apple continuity protocols, and we found that they were affected by a large number of privacy issues. Here I'm only presented 4 of them, but there are way more than that. So it includes tracking, inferring smartphone activity, discovering email and phone numbers. And the bad news is that all those messages, all those issues, they are affecting a pretty large number of devices. So all the devices of Apple are affected, but also device of affiliated companies, which we estimate around 1.5 billion devices worldwide. This is another example that security by obscurity does not work. So they've created their own protocols and they try to include some protection, but they were not, we believe, properly reviewed, and so they have many issues. So maybe they were hoping that by not disclosing how the protocol were working, maybe nobody will find problems. You may be interested in passing those messages. If you want to pass the BLE messages that your devices are sending, you can download the software we have released. Using that, you will be able to see in Wireshark the details of all the messages, understand what your device are saying over Bluetooth Low Energy, and it's quite easy to do with a Bluetooth dongle. So try to do that and have fun. Before finishing, I want to mention that, of course, we notified Apple in advance, so in May 2019, about that, just before we submitted the first version of our paper. So they received our notification and they acknowledged it. But we noticed that they haven't fixed many things, and nothing at all actually. Most of the attacks are still valid as of today. We made recommendation how they could reduce some of these attacks. They did not consider it. So the question is, why are those problems still around? Maybe they are too difficult to correct. For instance, HomeKit protocols, so they are inside smart home appliances, and as you know, Internet of Things, updating the firmware is not something that is done often. So changing the protocol will break all those devices. So this is maybe why they haven't done it, at least for the HomeKit protocol. Or maybe the problem was not serious enough. So since we notified this, there were more than 10 updates that have been done on iOS, and only one specific issue has been corrected. I think it's something to do with the battery level. I need to check again. But all the other problems, they are still around. So yeah. Apple is not, Apple is often advertising that they are very careful about the privacy of their users, but here we have a good example that maybe It's just it's just what they say and not what they do. All right, this is the end of my presentation. So I want to point to the original paper from which this presentation is extracted. Though this paper has been published at the conference PETS in 2020. And if you want to know more about it, and if you have any idea to share with us, please get in touch with us using the following email addresses.
Okay, thank you, Mathieu, for the great talk. I will start with a few questions. How long does it take to do all this fancy analysis of the Bluetooth low energy?
Actually, it didn't take that much time. Once Guillaume identified the possibilities offered by, I mean, the three methods that we discovered, especially the one with the disassembly, it was pretty quick. It was discovering the thing was not so long. Then doing some experiments were a bit longer. But I think in total we worked maybe a month full time doing the practical thing, and then there was, of course, the writing of the paper.
May I ask a second question? Is about the tracing aspect. You have the possibility to identify who is moving with the Bluetooth low energy, and you say that adding a random is not enough, if I understood correctly, because you have extra kind of side channel or other information that can identify the person. But you didn't propose any idea of countermeasure. What should we do for avoiding this? Because I think it's a vanished problem.
Yeah. So yeah, the problem I've mentioned is pretty common in wireless network that implements address randomization. So Bluetooth low energy is doing it. Wi-Fi is also doing it. So some vendors are implementing it in Wi-Fi. So the address is changing randomly. But as you said, and as I've showed with a specific example in a presentation, if there are other elements inside the frame that can be used to link to consecutive addresses, I mean, you basically, kill the address normalization purpose. And so several works I've been looking at. So there is a group of researchers, including myself and others, that have been working on this topic for now more than 6 years. And we came up with a pretty simple list of recommendations. Actually, there is now documents IEEE for specifically for the Wi-Fi standard that gives a number of rules that should be implemented. Those rules are quite simple to implement, but like for instance, if you have counters in your frame, you need to reset them to a random value whenever you change your address. This is one thing, and also you should not obviously include other identifiers in this frame. And if you include identifiers, you need to rotate them at the same time as you rotate your device address. So you need to do that. I mean, the requirements are quite simple to express, but in practice, they are the vendors that do not consider those issues, that make stupid mistakes. And then there are vendors that are aware of the problem and try to do something. This is the case of Apple, not in this specific protocols, but you may be aware of the contact tracing application that have been released recently to try to limit the spread of the virus. And Apple and Google, they presented, they've introduced their own system in which they have they also use Bluetooth energy to transmit identifiers. So there is the Bluetooth address that is used, and inside the packets, there is an identifier used for contact tracing. And they thought of, okay, we need to rotate those two at the same time. It's part of the specification, and they actually do it inside in their implementation. But in fact, they try to do it, but sometimes the synchronization is not exact, and there is a small overlap, and it breaks everything. So there is a paper from Vodney and Vanu on this topic. No, not the paper, actually a video. I can send the link a bit later. That shows that this is happening. So it shows that the rules are simple, but even the vendors that are controlling fully the OS, they are not capable of doing it, implementing correctly the synchronous rotation of those identifiers. So yeah, we need to work more on that, on the implementation and the verification side.
Okay, thanks. One quick question, so two questions that I will summarize in one. It's about the voice command on Siri. Does it recognize any sound, and can you get the command of the victim voice?
So it does not recognize any sound. So you need to start to trigger this mechanism. You need to start initiate it saying, "Hey Siri," to your computer, to your smartphone or whatever, and then it will record a short sequence. And from this short sequence of voice, it will compute the hash. But like I said, 16 bits is not a lot. So we performed an experiment in which we had a dictionary of spoken command that we spoke in front of the Siri. We recorded the hash, and we tried to later on recognize which command was spoken. And we found out that yes, because there are variation in the voice, and also because the set of the different hashes is small, there are a lot of collisions. So sometimes you may confuse. So for instance, if I say, "Hey Siri, call Mary," can be confused to "Hey Siri, call Mark." So you can infer, if you know, if you have a short list of comments, you could recognize which comment is sent. But if you have no idea of the comments that can be sent to your Siri assistant, it may be more complicated.
Okay, thank you, Mathieu. We'll now go to the next talk given by David. Bye-bye.
Bye.